Okay, Assalamualaikum warahmatullahi wabarakatuh. We are from Group 1 and we will present about experimentally major losses in pipe. Now I pass on to the next presenter.
Okay, so hi, I am Aina Alia and I will present for the report summary. This experiment 3 is an experiment about major losses in pipe to determine the pipe friction factors, which is F, also known as resistance coefficients. The total energy loss in the pipe system is the sum of the major and minor losses. Major losses are associated with frictional energy loss that is caused by the viscous effects of the fluid and roughness of the pipe wall. Major losses create a pressure drop along the pipe since the pressure must work to overcome the frictional resistance. In the equation, the friction factor, a dimensionless quantity, is used to describe the friction loss in the pipe. In laminar flows, F is only a function of the Reynolds number and is independent of the surface roughness of the pipe. In fully turbulent flows, F depends on both the Reynolds number and relative roughness of the pipe wall. In this experiment, F will be determined by using several methods and equations, and also will be discussed in the later part. Next, I will pass to the next presenter.
Hello, I'm Leodin. I will continue on with the theory part. In turbulent pipe flow, which is 4 times 10 to the power of 3 and until 5 times 10 to the power of 5 between 2 points for the horizontal pipe, which has constant internal diameter di with no minor head loss HLM accounted, whereby the total head loss HLT equals to major head loss HL. The pressure loss P and major head loss HL using Bernoulli's equation could be determined experimentally as follows as shown below, where P equals this pressure loss between 2 points P1 minus P2, which is in Pascal. F is the coefficient of pipe friction, which is dimensionless. L is the length of the pipe, which is in meter. Di is the internal diameter of the pipe, which is in meter. Rho, density of the flowing medium in kilogram per meter cube. V square, square of the speed of flowing medium, meter cube per second square. G, gravity constant, the usual 9.81 meter per second square, and HL, which is major head loss in meter. For the turbulent pipe flow, the pipe friction coefficient depends on the equivalent pipe roughness and Reynolds number. For the equivalent pipe roughness, which is in epsilon, it is shown, we can see that table in the table 1, which is given in feet and millimeters. This is what we call the Moody's chart, which we can later determine the coefficient of friction. We will need the absolute roughness just now over our diameter, and we will also need a Reynolds number. For the Reynolds number, we can calculate using VDI over mu, which is V is the speed of the flowing medium in meter per second, Di is the internal diameter of the pipe, and mu is the kinematic viscosity of flowing medium in meter cube per second. For the kinematic viscosity, we can see its value according to its temperature in the table beside it, in the table 2. For the speed of flowing medium, we can calculate using the formula in equation 4, where Q is the flow rate of flowing medium in meter cube per second, Di is internal diameter of pipe in meter. This three formula is also used to find the coefficient of friction, which is the top one is called the Blasis formula, the middle one is called Colebrook formula, and the third one is called Moody's formula. All three can be used to calculate the coefficient of friction. Now I pass on to the next presenter for the procedures.
I'm missing. I will continue for procedures. First, connect both the feeding and return host to the tested pipe section. Next, the manometer tubes at one of the two tubes manometer are fixed, which is one in and one out up to the tested pipe section. After that, the main switch and the pump are switched on. The control valve is opened slowly to allow the circulation of water through the tested pipe. When the reading of actual flow rate reaches 2 meter cube per hour, open and turn the black color ventilation valve on the top of the tube manometer to anti-clockwise dilation in order to release all the bubbles in the system. Close the black color ventilation valve and turn it to clockwise dilation if there is no presence of bubbles. Next, the pump is switched off and control valve is closed. Moreover, the white color ventilation valve on the top of the tube manometer is opened slowly until the preset minimum reading of the tube manometer for galvanized steel and PVC pipe reaches 25 mm, 1 mm for copper pipe, 20 mm for PVC pipes, and 32 mm for PVC pipes. Furthermore, the control valve is slowly opened until the water level at tube manometer H1 reaches the maximum while H2 at minimum level. The manometer's reading of H1, H2 temperature and actual flow at the load photometer are recorded. By adjusting the opening of the gate valve, the actual flow is reduced to 5 different values. Hence, all the readings of the multi-tube manometer H1, H2 temperature and actual flow rate are needed to record again. Take note that the minimum value of actual flow rate should around 0.2 meter cube per hour. Next, the experiment is continued by moving the manometer tubes at the two tube manometer to differential pressure section P1 inward and P2 outward. Make sure to record the reading of differential pressure sensor that show at the digital display for 5 different values of actual flow rate which is when the value of flow rate was 2 meter cube per hour and 0.2 meter cube per hour. It is a must to ensure there is no any bubbles contained in the system. The ventilation valve is closed when there is no presence of bubbles and all the value of actual flow rate, temperature and differential pressure reading are recorded. Lastly, all the manometer tubes are removed from the system, the gate valve and pump are turned off respectively before pressed the feeding and return hose to another pipe section. Repeat the steps to step at. After the experiment is finished, all the manometer tubes are disconnected from the system. The gate valve is closed, the pump and main switch are switched off. Let's pass to the next presenter.
Okay, so next we have result analysis. So for the calculation part, we determine the F by using 4 different methods, which are Moody's chart, Blaze's formula, Colbert formula, and also Moody formula. Before we use the equations, we calculate the Reynolds number by using the data given. And based from our calculations, all of the flow are turbulent flows. Then we also need to calculate the equivalent roughness divided by the diameter of the pipe. Then for Moody's chart method, we use the chart to obtain the F, while for Blaze's, Colbert, and Moody formula methods are calculated by using their own formula. So after we obtain the F's by these 4 formulas, we calculated the heat loss by using the F average. So this is the F's and heat loss obtained from the calculation from each types of pipe. So this one is for galvanized steel pipe. Next we have copper pipe. Next we have PVC pipe 1, which has diameter of 17 millimeter. Next we have PVC pipe 2 with the diameter of 12.4 mm. And last but not least, we have PVC pipe 3 with the diameter of 38.2 millimeter. Next, I will pass to the next presenter for the discussion part.
Okay, for discussion part one, I will continue this part. So number one, compare the coefficient of friction F for each of the tested pipe in your experiment with the coefficient of friction F from Moody's chart and a calculation using a formula of Blasius, Colebrook, and Moody. Explain the possible reasons for the difference in their values. First and foremost, this is the coefficient of friction calculated using each of the formulas mentioned for each pipe. This is for galvanized steel pipe, and copper pipe. This is for PVC pipe. The first one, PVC pipe second, and the third, PVC pipe. As for the reason, from the table, it is shown that the values taken from Moody's chart, Blasius equation, and the Colebrook equation seems to have similar values, while Moody's equation give a value that deviates from the earlier three methods. This is because in the Moody's equation, the part where 10 the power of 6 divided by the Reynolds number makes the difference here, because our Reynolds number does not exceed 10 the power of 6. Next, presenter for the second part and third part of the discussion.
Hi, I'm Adrian. Now I'm going to discuss the second part of the discussion, the rank of the pipe in ascending trend based on their major head loss value obtained from the experiment. And we also explain briefly on the factors that influence the pipe ranking selections. From the results, we get the ascending trend based on their major head loss starting from PVC pipe 3 0.0389, PVC pipe 2 0.0951, galvanized steel pipe 0.133, PVC pipe 1 0.244, and the last copper pipe 0.2952. There are a few factors that influence the major head loss of the pipes. The major loss for the flow through the pipe is due to the frictional resistance between the adjacent fluid layer sliding over each other. This resistance arises due to the presence of viscous property of the fluid. As we can see from the formula calculating the major head loss, the F is represent the friction factor. The smoother the inner surface of the pipe, the smaller the friction, the lower the head loss. Thus, since PVC pipe is smoother than steel and copper, it has a lower head loss for identical conditions. Next, major head loss can be influenced by the velocity of water in the pipe. The higher the flow rate of the water in a given pipe, the greater the head loss due to the friction. Friction increases as the square of the velocity as shown in the formula. Lastly are the fluid density and viscosity, and these properties vary with temperature in such a way that they have competing influences on the head loss. And next is the third part of the discussion, factor contributing to errors or inaccuracy in experimental data and the possible recommendations to improve the existing results. During this experiment, a few errors were made. To begin with, due to the existence of an air bubble in the tube. All of the data given is slightly inaccurate, meaning that the value in the manometer is incorrect. However, it can be avoided by making sure that there are no air bubble in the manometer before we starting the experiment. Furthermore, the observer eyes are not immediately perpendicular to the manometer reading. In other words, this is referred to as parallax error. This can be reduced by ensuring that the eyes are perpendicular to the manometer reading while taking the reading. Finally, if the rubber tube is not firmly connected to the inlet or outlet valve, fluid leakage may occur. To ensure that the rubber tube connection is near enough, the flow rate in the pipe should be the same as the flow rate from the water meter. The finding would be more accurate if all of these steps are taken. Next, I'll pass to the next presenter.
Last, I will continue to conclude our experiment. The pipe friction factors are very important in engineering-related work because they measure the head loss caused by a fluid as it flows through a pipeline system. They have subtle variation and parameters from this experiment, such as the value of coefficient friction that we discover by using the multimass Bezier-Corbut and Moody formula. The Corbut equation is the most accurate of all these equations since it can be used to measure of smooth and rough pipes, while the Bezier equation is more suited for calculating smooth pipes. We can calculate the value of the head loss in this experiment based on the calculation we have conducted. The head loss for galvanized steel is 0.113 meter, copper pipe is 0.2952 meter, PVC pipe 1 is 0.244 meter, PVC pipe 2 is 0.0951 meter, and PVC pipe 3 is 0.0389 meter, respectively. As a result of the findings, the experiment goal was achieved. That's all for our group. Thank you.